Okay. Well, my name is Omar Azami. I'm with the Peer Tutoring Lab at UT Dallas, and I'm a physics content specialist. And from what I understand, many of you are going into physics 2325, which is 2000 based calculus based physics. And a lot of the time, the coverage of math topics needed for the class is not necessarily the way it's covered in the math department, which is fine, but there's still things you need to know before going into physics 2325. And today on the agenda, we'll do more practice problems. If we get done with it early, I'll contrive some. We're going to go over the definition of scalars and vectors. How do you go down?
You have to go to your PDF.
Oh yeah, PDF. The terminology of vectors. We're going to add vectors graphically from what you learned in high school, adding them head to tail. We're going to subtract vectors graphically. We're going to have a trigonometry review so we can then learn to add them component-wise. Then you'll hear about something called the dot product and the cross product, which are two sort of operations that you can do with two vectors and get a geometrical result that is actually meaningful. Without further ado, let's get started. This is your typical definition of scalars, and you've probably heard it a million times. Scalars are single numbers with just a magnitude, the absolute value. And vectors are numbers or pairs of numbers that have both magnitude and direction. I'm sure at one point you heard that temperature is a scalar, and then you wonder to yourself, how can things have negative temperature and still just have a magnitude? So that definition is obviously, it leaves something to be desired. So we'll go on to a better definition of that. Scalars are quantities that can be completely summarized with one number, whether it be positive or negative. Big distinction. Vectors, on the other hand, are quantities that in limited cases can be completely summarized with one number, whether it be positive or negative, but are more generally described with 2 to 3 numbers as a directed arrow in space. Here are some typical definitions, typical examples of scalars: length, mass, speed, energy, temperature, which is related to energy but is not quite the same thing. And your vectors: displacement, velocity, acceleration, momentum later, angular momentum later, etc., etc. So I talked earlier about vectors being directed arrows in space. You can move them around in a parallel fashion and they still retain the same geometrical significance, if you will. But it's still important in physics to know where the force may be acting on. Parallel vectors, as you could probably guess from driving on roads, parallel vectors have the same direction. Anti-parallel vectors have opposing directions. That makes perfect sense too. Equal vectors, on the other hand, have the same direction and magnitude. If you want to add vectors graphically, right here we have two vectors, A and B. And what you want to do is move in this instance, the tail of C, the end without an arrow, to the head of A, and then draw an arrow from the tail of A to the head of B after you've moved it. I think I'm moving pretty fast here, so I'm going to slow down. Are there any questions? Okay, we were told in an email this is for Physics 1301. can we go to the last slide again? Which one? It is for both 1301 and 2325. There's not actually going to be any calculus in this particular lecture. The parallel vector slide, of course. Let's see. By the way, there should be a copy of these slides available for everyone to download in the chat or in the shared files or something like that. Parallel vectors have the same direction. They point in the same way. Anti-parallel vectors, they're kind of like parallel vectors, but they're the exact opposite. Equal vectors have same direction and magnitude. Same length, same direction. Where can we get these slides? I thought I shared it.
Yeah, slides available for me download stuff and post a link.
Yeah. I mean, can I? Is there any?
No, you can't. No, you can't. Okay.
I can't share files.
You can share a file. They can download.
Oh, okay. Let's see. So I have to text this to you on this thing.
Yeah, just check.
Okay. All right, guys. I'm going to. Yes, we can go over scalars and vectors with examples as soon as I put the slides somewhere that you can download them. Oh, someone was able to download the slides. Where?
Mine was wrong.
Okay. All right. So can we go back to scalars? Okay. Yes, let me figure out how to put the slides somewhere. Was anybody else able to download it? All right. Can those of you who are able to download it tell other people where they can download it? All right. In the meantime, I'm going to go back to the lecture. Can everybody see my screen? We're on the vector terminology. All right. So let's go back to examples of scalars and vectors. Length, well, that's naturally how long something is. All right. If I am 5'9", if I lay down in different directions, east or west, I'm still the same length. I'm still the same height. but I'm pointing in different directions, and that's what I guess displacement is. The distance, a directed distance from one place to another. Direction matters. Directed arrow in space. Mass, it doesn't really make sense to have.
No, you're not sharing your PDF.
I'm not sharing my PDF. Okay.
Yeah, go back to Chrome and go back to share content area. The good icon.
Okay. Share.
Yeah. Share.
Okay. Sorry about that. I'm really sorry. Length. Velocity is contrasted with speed. I could be going.
Wait, hold on, it's not share. Not share. Go back and try to share.
Is it sharing now?
It is, yes.
All right. Velocity is, you could be going 30 miles towards 30 miles per hour towards California. You could be going 30 miles per hour towards New York. Direction matters because you're describing something more specific. Speed is just going 30 miles per hour wherever you want. Energy, that's a hard sort of topic to really nail down. It's actually a very rich topic, but I guess one way to describe it is the sum total of quantity of motion. And that's related to temperature, which is pretty much that of atoms. And are there any other questions regarding that? Is my screen still being shared?
Give me a second.
Okay. I'm going to all right. Now let's go on to, let's go back to parallel vectors. They have the same direction. Anti-parallel vectors have opposite direction. Equal vectors have same direction and magnitude. Now we're going to go back to adding A and B. The one part of the vector that you want to distinguish from the other is the head and the tail. As you can see, there are little arrowheads on what you might call the head of an arrow. The tail is naturally the end that does not have one. When you add two vectors A and B, as shown here, you want them to share two tails to initially start out. And then what you want to do is move the tail of one vector to the head of another vector. In this case, we're moving the tail of B to the head of A. And then we're drawing an arrow with a tail starting at the tail of A and ending at the head of B after we've moved it, after we've moved B. This process could have been done the same way if we added B to A. if we add B to A, we're going to move. We're first going to have the two vectors share a common origin at the tail, and then we're going to move the tail of one vector to the head of another vector. In this case, we're moving the tail of A to the head of B, and now we're drawing from the tail of B to the head of A after we've moved A. So if we take a look at these two comparisons, we see that they are the same vector. C equals A plus B, C equals B plus A. That means adding is commutative. Are there any questions? Why do we have to do the first part tail to tail? That's a good question. I guess it could always start out in the proper configuration of head to tail, but usually it doesn't, because if you think about it, at least in a physics perspective, if two forces are acting on a body, say there's two ropes, one pulling up, one pulling to the side, they're both influencing the box, so to speak, in different directions. They both start at the same place, the box. But what you want to know is that net effect on the box, it's going to, you're going to add the vectors head to tail to see what the ultimate effect of it is. Does that help? Okay. I want to talk about one operation we can do with vectors, and that's multiply by a scalar. And as the name suggests, it scales the vector. It can scale it in a forward direction or backwards direction, depending on what you want to call forwards and backwards. Let's start off with this vector A. If we multiply it by the number 2, just the number, not a vector, just a number, just a scalar, 2. We double its length and retain its direction. If we multiply it by -1, we retain its length and reverse its direction. I guess there's a lot of things you do with vectors called quote-unquote multiplication or quote-unquote taking a product. But this one is probably the multiplication of regular numbers, multiplying by a scalar. There are two other operations we will define later. But the reason I brought up multiplying by -1 is because that is in fact how we subtract vectors. See, right now we have A minus B. We start off with them tail to tail. And then, like I said, if we want to find A minus B, we have to do A plus minus B. So multiplying by 1 retains the length, reverses the direction, and now we're ready to do the head to tail business. So I'm going to move minus B, the tail of minus B, to the head of A, and then I'm going to draw an arrow from the tail of A to the head of B to get what A minus B equals. Again, that's the reason I brought up scalar multiplication by -1, so that we could then define vector subtraction. We don't have to make B negative. I'm giving you an example of if B is given to you as negative. how would you do that? Because think about it. If you want to know whether the force is going up or down, you're going to have to attach a negative sign to it sometimes. So this is what we're doing. B is made negative for the sake of this problem. In the course of doing problems yourselves, you're going to have to make that judgment call. This is just defining a mathematical operation. So let's go back. Because A plus B is definitely not the same as A minus B. So we need to find out how to define A minus B in a way that takes advantage of the definitions we've come up with so far for addition and scalar multiplication. There is also another way to add vectors, but first we must consider their components. Here we have a vector v in the xy plane. Vx is the magnitude of the cosine theta, where theta is the angle the vector makes with the positive x-axis, and y is the magnitude of v times sine theta. And this is just notation. V is often expressed in component form in the following manner. You use angle brackets as ordered pairs separated by a comma, and sometimes it's called Vx I hat plus Vy j hat. J hat being the unit vector in the y direction, I being the unit vector in the x direction, and its magnitude is defined as usual by the Pythagorean theorem, which is also related to another operation which we will get into later. If you want to know the angle it makes with a positive x-axis, you just do the tangent inverse of Vy over Vx. However, you should be mindful of the actual geometry that's in place, because tangent -1 has some discontinuities. So you need to look at it and interpret it geometrically. So in the next slide, we show you all the different variants that it could take. In quadrant 1, you can see both the x component and y component are positive. You can make, in quadrant 2, we see that the x component is negative, the y component is positive, so on and so forth. So the angle that it makes with the positive x-axis is not necessarily the angle it makes with the x-axis in general. You really have to look at your triangles to see what angle is being considered. Can we do this problem without making b negative? We can go back and go over basic vector addition if you want. Is my screen still being shared? So let's not make b negative. Let's start out with a and b sharing tails. And then let's move the tail of b to the head. Let's move the tail of a to the head of b, and then complete the triangle. You'll see that a plus b is b plus a if you also do it the other way. This sort of makes sense. If you want to think about this physically, if someone's pulling on you from above you and someone's pulling on you from the side of you, you're going to go somewhere in the middle. Is the head of C the same place as the head of A? Yes. So after we've talked about components, I want you to be mindful of where exactly you are in your coordinate system. X is not always cosine theta. Y is not always sine theta. You need to know what opposite and adjacent mean and adapt it to the problem at hand, which we will get into in the next few days. The generalization of this is that a vector in 3D space as opposed to 2D space has 3 numbers instead of 1 number. And in addition to our usual X and Y component, we have a Z component. And our usual I hat and J hat unit vectors, we now have a K hat in the Z direction. Here is an example. We're going to add 2 vectors component-wise. A we have as -3, 0. B, it has a magnitude of 4.5. It makes an angle of 37 degrees. And then when we decompose it into cosines and sines, we get that the X component is 4.5 cosine 37, and the Y component is 4.5 sine 37. And now when you add them up, this is how you typically add vectors. You add up the components. Because I don't know about you, I can't draw that well. We have C equals A plus B, which of course A has both an X and Y component, and B has both an X and Y components, and we add the components together respectively to get the components of the sum. If C equals A plus B, then it equals 0.5938 and 2.708. And if we wanted to find the magnitude of C, we would just use the Pythagorean theorem, which is related to the dot product, which we'll get to later. And of course, if you wanted to find the angle, you do your usual tangent inverse. Of course, you want to be mindful of where it is. And in this sense, it's in the first quadrant, which makes sense that it would have an angle of less than 77.6 degrees. Yes. Okay. -3 and 0. Its X component is -3, and its Y component is 0. Can I see it? Yes, it is shared. Vector A. Oh, I apologize. I forgot to mention vector A. As you can see, A is given to us as -3, 0, because its X component is 3 in the negative X direction, and it has no upward component. And when you add them component-wise. You'll add -3 plus 4.5 cosine 37 and 0 plus 4.5 sine 37. And when you punch that into your calculator, you'll get these numbers, these magnitudes, and these angles. I'm sorry about that. I should have. Would you ever add AI, BJ, and CK together? The thing is, you can add them together, but it's not going to be anything meaningful. Like if you add like 3i plus 4j, you'll get 3i plus 4j, because the j hat component is independent of the x hat component. Could you go back to the previous slide? Yes, of course. This one? Is this a slide? Yes. Okay. Yes, here we go. Can we, is this good or? All right, let's move on. Still a lot of good stuff to get to. And thanks for slowing me down and expressing when you need some help and when I need to clarify things. So yes, these are the components. This is how you algebraically add vectors, unless you're just like a perfect artist. But I'm not. Nobody is. Let's continue. So now if we plot c equals a plus b, we'll get that exactly as what we have up here. C equals 0.5938, and all that stuff. I want you to realize that this is exactly what we would have gotten if we had done it graphically with a head to tail distance. See how these head to tails and a plus b and b plus a sort of yield the same vector as c? I just want to show you the equivalent of these two approaches. Obviously, one is more advantageous when you're actually doing problems, and that's adding components vector-wise. Adding vectors component-wise, rather. Is it technically the average of both vectors? Not that I could. What? It's sort of, I can see, I've never heard of it said that way, so I don't want to say yes, but I can sort of see what, as in that, like, it's sort of weighted between the two. So I think that's an interesting sort of outlook, but in case I'm wrong mathematically and technically speaking, I don't want to say yes, but I can appreciate your perspective. The difference between a plus b and the absolute value of a plus b is the absolute value of a plus b is its length or its magnitude. A plus b is just what it is, what the vectors actually is. The magnitude of a plus b is just its length. The bars around it and whatnot. As you can, that's just the Pythagorean theorem. It's squared components added and taken the square root of. So, all right, right on. So let's move on to something called the dot product. The dot product is, I don't want you to look too far into this name as if it's supposed to be completely analogous to everything you've learned about multiplication in regards to numbers that you're already familiar with. You had to call it something, we call it the dot product. Also called the scalar product. If you have two vectors, a and b, which have components ax, ay, and az, and bx, by, and bz, you multiply like components together and add the result. And you might ask yourself, why would you do that? Well, it actually has some geometrical significance. I want you to take a note that if we replaced B with A and took the dot product of A with A, we would get its magnitude squared. And the reason I put that cosine 0 there is because it's equal to 1. But down below, we see that this formula generalizes. So we have A dot B equals the magnitude of A times the magnitude of B times the cosine of the angle between them. And we're going to prove that using the law of cosines very soon. The entire reason such a thing was invented is so that we can quote unquote project vectors onto other vectors. So going down, I just want to make a quick remark about unit vectors. A hat is the unit vector of A, and it's defined as A over its magnitude. So A over its magnitude is just the square root of its dot product with itself. You can see right now here, A in red has a longer length than its unit vector A hat. That's typically the case. You can have vectors shorter than 1, but it's not always useful. And from the law of cosines, we know that this A minus B side, which we've done in a vectorially correct sort of way, is equal to A squared plus B squared minus 2AB cosine theta. But we also know that the magnitude of A minus B squared is equal to the dot product of A minus B with itself. And when we FOIL and compare like terms, we see that A dot B is equal to AB magnitude of A times the magnitude of B times the cosine of the angle between them. There's also another thing called the dot product. I mean the cross product or vector product, unlike this scalar product, also called the dot product. And before we go over that, we need to go over this operation of taking quote unquote determinants of 2x2 matrices. We have a matrix here, which is A, B, C, D. And when we want to take the determinant of it, we put it in these elongated bars, and we take the product of the, I guess what you'd call it, the main diagonal, and subtract the product of the non-main diagonal, basically AD minus BC. And that relates to the thing that we're going to define next, called the cross product. This is a pretty elaborate expression, but basically what it's meant to do is generate a third vector from two vectors that is quote unquote at a orthogonal to both of them, or at a right angle to both of them. This is fairly common in rotational mechanics to define torque and angular momentum, things like that, which if we have time we'll get to. If you look at the x component, that now we're defining a C equals A cross B. We're striking out the x column and top. So we now have the determinant of what's left over. And when you take that determinant in light of the definition that we gave you earlier, this is your ultimate expression, AY BZ minus AZ BY. Now CY, the Y component of C, which is A cross B in our problem, there's a trick you have to watch out. It's not just the determinant, it's the negative of the determinant of striking out the top row and the second column. Second column is y is second. So after you take the determinant and then you negate it, this is the expression that you will get. And something very similar for CZ. We strike out the top row, third column because Z is third, and then you take the determinant of what's left over. This time it does go back to the positive determinant. So I want to talk about the right-hand rule. Okay, there's an easy way of visualizing with your fingers what this operation is doing. What you're supposed to do is put your index finger in the direction, I wish you guys could see this, your index finger in the direction of the first vector, your middle finger in the direction of the second vector, and then you stick your thumb out. And that is the cross product of your vector, at least the direction of it. There's a let's see. Unlike dot products, which are commutative, A dot B equals B dot A cross B is not equal to B cross A. So one thing is, for this one, you're going to have to stick your hand upside down. If you find at any point you're having to break your fingers or your wrist in order to find out which direction a force or torque goes, you just need to move your hand over, turn it around a little bit, and you'll be fine. You don't need to break your hand. So the index finger is where B will be. The middle finger is where A will be. Then you stick your thumb out and it will point down. And that is your B cross A. So let's go on. That's the visualization of what's happening. I want you to realize that the cross product is at a right angle to both of the original vectors, which may or may not be at a right angle with each other, just a general theta. And there's another interpretation of this, which says that the area of the parallelogram subtended by two vectors A and B is equal to the magnitude of the cross product, which is then equal to the magnitude of A times the magnitude of B times the sine of the angle between them. Any questions so far?
Are you going to do examples later? Or?
Yeah, do one. I brought one. Is there anything? Well, torque for one thing. Torque equals the radius cross product with the force. Find out how fast something is rotating or how fast its rotation is changing. It's also used in torque is equal to R cross F. We're going to work some problems here. Okay, let's, I'm going to work a problem, and I will also cover the formula for torque again. Let's move over to OneNote. Okay. This is one node. Okay, let's do this. I've never used one node in my life before. Where's the eraser? Okay. All right. So, can everybody see my page? Elliot, can you see my page? Yeah. Torque, often given with the capital Greek letter tau, is equal to the radius cross the force. And one thing, I guess I'll give the most simple example. Say we have a pivot right here, and a pivot right here, a pivot right here, a long beam, and a force is pushing down on it. You want to know the effect of its rotation. So here is the point at which it is being rotated, like a seesaw, for instance, and this is the angle between them. Or really, if you move, you technically want to keep R and F together. So R and F would really be here. And for the sake of the cross product, the angle between them is this bigger angle right here. So naturally, the further you are away from something, the easier it is to push it and make it go fast. So that's that. So let's do a cross product example. What we're going to do is I want everyone to take the cross product of A with B and tell me what it is. Let's call this B. I should probably give you maybe about 3 minutes. About 3 minutes to do this. All right. Okay. Should I go ahead and do it? All right. Well, let's go over here. We have C equals this is our determinant setup. We're going to cross out rows and columns as needed. 12, 0, 0, 14.4, 10.8. Okay, so for CX, we're going to cross out the top row and the first column because X is first, and then take the determinant. So 0, 0, 10.8, and 0. And if we multiply the diagonals and subtract them, the answer for this one will be 0. So we have 0 for our X component. Okay, for our CY component, we're going to take the negative of a determinant by crossing out the top row and the middle column because Y is in the middle. And of course, that is also going to be minus 0, which is the product of the diagonals. And then, so I'm just going to put 0 here. And then for CZ, I'm going to cross out the top row and the last column. Which is going to be minus 12 times 10.8 minus 0 times 14, which is 0. So we get my calculator. Yes. This right here? Yeah. I'm just going to go ahead and call it 130. It was something like 129.6. And now, ultimately, what what is this? Negative 12 times 10.8. It's pretty close to 130. I'm just going to call it minus 30. And what happened now? Okay. So if we go back to our original drawing, which is not original because I'm drawing it right now, A would be negative 12 somewhere in this direction. X and Y would have, for B, would be somewhere here. And C, of course, would be, well, actually, it would be in the opposite direction if you use the right-hand rule. C, if you take your middle finger at A, put your index finger at A, align your middle finger along B, stick out your thumb, it points down. So this is C equals A cross B. And just to get in the habit of doing these things, I'm going to give you some other examples that help you just get used to the mechanics of the mathematics with vectors. So I want you to find the magnitude of A. And again, A is equal to negative 12, well, get it, well. I mean, the answer is obvious, but pretend it wasn't. And tell me what someone would do, 2 ways someone would find the magnitude of a vector. And they're ultimately the same, but they might be called 2 different things. Square each component, add them up, and square root the whole thing. That's absolutely correct. So when we multiply components together, what were we using earlier? It's the dot product. The dot product is almost exactly that. If you recall, A dot A equals AX plus AY plus AZ, which is ultimately equal to AX squared plus AY squared plus AZ squared. So this is really just, the dot product is really kind of sort of just the Pythagorean theorem. So obviously if you wanted to do A, you would do negative 12 squared plus 0 squared if you want to be pedantic about squaring your zeros. And you would have, of course, 12 as your final answer. I'm going to do the same thing with B and C. We get that this is equal to exactly 180. No, 18. 18. It's a big difference. Well, now that we have the magnitude of A and the magnitude of D, I think we should just go ahead and find the magnitude of C. And then from there, find the angle between A and B. Well, C is also sort of trivial because it only has one component. Let's see. Well, dotting a vector with itself is kind of like multiplying a vector with itself, but it's not limited to just that. The best, I wouldn't think too hard about it. I would just accept that it's been defined because it has a very useful geometric interpretation. And let's see. So now that we have that, let's we know that let's see. You know that the magnitude of C equals magnitude of A cross B, which is equal to A B sine theta of the angle between them. Okay, well, we know that I think one way we can go about this is we know that sine of theta equals magnitude of C over A B. And I guess we can just go ahead and make that a sine inverse at this point. What is sine -1 of 130 over 18 and 12. Make sure for this problem, when you find the sine inverse, that your calculator is in the right mode for the question. Usually it's radian, but for now we're doing degrees. Wow, it's 37 degrees. I must have thought about that.
Yeah, explain my sign is in there.
Well, where?
Chat.
Yeah, go to chat.
Okay. This is actually why this formula has sign in it. There is a pretty elaborate, if you define a C is equal to A cross B, and then you do a proof, law of cosines, it's a long proof, but it's a common proof. You can see that this relationship holds. And as Les says, you can also think of it geometrically. And yeah, I think we should, as Les says, we should explore this idea more of the geometrical interpretation instead of the really hard proof, which is not too hard. It takes some time. Let's see. What Les has drawn here is B, A, and we know that the cross product, or at least the magnitude of the cross product, is equal to the area of the parallelogram. And you might ask yourself, well, the parallelogram's area, given A and B are the same, wouldn't that depend on B sine theta? And that's the height. And if you ahead of time accept the geometric interpretation of the cross product, then you can see it corroborates the definition for the magnitude C, corroborates that notion without getting into a really difficult proof, which I think I could figure out off the top of my head, but I haven't rehearsed. Does that work? All right. All right. So, yeah, that was because I got done with it. So we have that the angle between A and B was 37 degrees through now let's see if we can corroborate this result with dot products. So if you remember, we actually went through a proof for this one because it was simpler. A dot B equals A B cosine theta. And just to copy what we have down already, what is it? Minus 12, 0, 0. P was So we have that the magnitude of A, if we look up, well, the magnitude of A is obviously 12. Is obviously let's take the dot product. A dot B equals minus 12 times 14.4 times plus 0 times 10.8 plus 0 times 0. Negative 12 times 14.4 equals negative 172.8. Okay. Let's see. We knew that A equaled 12 and B equal to 18. Hopefully we'll get a 37 out of this, but I'm concerned about the negative. Theta equals cosine negative 1. Oh, cosine inverse. I'm getting 143 degrees, which is not actually that bad. You have to think about it. Again, use your geometric intuition. The angle between A and B, if you actually looked at them, it's going to be more than 37 degrees. It has to be. But you'll notice that 37 degrees and essentially 143 degrees, they are actually supplementary angles.
I feel like there might be a mistake somewhere because I guess for starters, these will add up to 180. They actually add up to 1. Did have 180, that 180. I think there's still one there somewhere. But I'd have to go through and see where it is. But because of this. I see that. So the issue with use timing was it can't be doing it on its own.
Yes, yes. The thing is, a lot of these trig inverse functions have domain restrictions, and you just have to be mindful of that, and you actually have to look out for it. It's not always the case that it will give you the correct answer. You have to be visually mindful of it. It's not always the case that it will negate something or negate the angle. Just to be clear, when we take a dot product, and our dot products and cross products the same. I would think they are complementary, but they're not the same. One gives you sine theta, one gives you cosine theta. Dot product, I don't think it necessarily has the interpretation of area. It's more of a projection thing. But there are connections between dot products and cross products, and they use some advanced vector calculus to prove the identities of, but they are fundamentally different things. Does anybody else have a question? If there are no more questions, what I can do is I can save this file and upload it to this chat. Oh, yeah. Okay. Is it in there? Yeah. Really? Oh, is this because it's going through you?
No, well, I guess Les downloaded it on top of it and then uploaded it.
Even my handwriting.
Oh, not the one.
Yeah, let's do the one. That's what I want.
The OneNote. I can do that later today because I'm going to do this challenging one.
Can I?
So when I do that,
can I do it right
now? If you can export it as a PDF, if you want to share it.
No, that's all I want to do. What?
Yeah. If you export it as a PDF, is that what you want?
Yeah.
That's what export. Whatever.
Like f of x. One minute.
Go to the. Here. Let's see what it looks like. It's nothing to that.
Looks like what we need it to look like.
Okay, that's good. Yeah.
So,
Alright, so then. Okay, let me. I guess I'll do it last time.
Google chat.
Yeah, we have a well, because we have a YouTube channel.
Okay.
So.
That's weird. That's
Why did it become a
HTML document.
Yeah.
That's strange.
Yeah.
Go to One Notebook.
That's right. Let's try that one more time. I've never seen that before.
Can
Well, what does it say?
I try something?
Yeah, go ahead. Yeah, try it. Well,
Then they're all going to do their own thing on it. So.
if you want, yeah. Because I think you can also download it here, but the thing is, it's
Yeah, it's kind of. This is from this is no, that's fine.
documents. Let's try it. Let's see if it works.
It's so strange how it was like an HTML.
Yeah, I've never seen that before. Did it work? Yeah, try sharing it.
Sure.
You can download it
And then, yeah, and then,
They do just download it from here.
yes, if you guys want to download notes, just click the download button. It's kind of near the top right of the screen. More media saturation. But there it is. Okay.
Kind of easier than I thought. It's your you can't export a PDF, but whatever reason
So is that,
share.
is that it? That's,
Yeah, Windows 10. Windows 10.
That's, I don't know, I just typed it. I just went down and that's the first one.
Yeah, yeah.
So, let's.
What was it? Something I hate better at, but it's but something I want to hate better. Maybe motivate the definition. But I don't know. I like it.
Yeah.
It's hard. It's hard. You can't go to Facebook, they know or they not. Yeah. Well, you could. That's a good idea. Motivate it.